So first we have to find the eigenvalues, right? Remember that if we have n distinct eigenvalues, then we know a priori that we are diagonalizable. Yeah? So let's compute the eigenvalues and see what we can get. To compute the eigenvalues, we really want to compute the determinant of A minus lambda I, which is the determinant of the matrix 2 minus lambda, 2 minus lambda, negative 2, negative 2, 3, negative 3 minus lambda, negative 2, 2, negative 2, negative 2 minus lambda. Yeah. By a little bit of magic, whenever we take the determinant, find the roots, by a little bit of magic, we see that the eigenvalues are 0, negative 1, negative 2. So we have 3 distinct eigenvalues. So what does that mean about the dimension of each eigenspace? The dimension of each eigenspace must also be 1, because the algebraic multiplicity of each eigenvalue is 1, right? So if we have 3 distinct, or if the dimension of each eigenspace is 1, then that means that a vector from each eigenspace has to be linearly independent, right? So we have 3 linearly independent eigenvectors, which means that we do have a basis of eigenvectors, right? So we are going to be diagonalizable in this case. Let's diagonalize the matrix. What do we need to diagonalize a matrix? Remember, a matrix is diagonalizable if A is equal to V dV inverse. We already know what D is going to be. D is going to be the diagonal matrix with our eigenvalues on the diagonal. Then the order doesn't matter. We'll just be sure to put the eigenvectors in the corresponding order. So the first vector in V would have to be the eigenvector corresponding to the lambda equals 0. The second vector in V has to be the eigenvector corresponding to lambda equals negative 1, and similarly for negative 2 here. But what do we need to do? We need to find a basis for each one of these 3 eigenspaces. So let's do it. How do we find a basis for the eigenspace corresponding to lambda equals 0? Well, as I'm sure that you've already done, we take our matrix 2, negative 2, negative 2, 3, negative 3, negative 2, 2, negative 2, negative 2. We augment 0 because we're finding a basis of this null space, right? Whenever we perform a little bit of row reduction magic, we hopefully get that this is 1, negative 1, negative 1, 0, 0, 0, 1, 0, 0, 0, 0, 0. Yeah. Here I see that x3 has to be 0. I see that x2 has to be free. And I know that x1 looks like it has to be the same as x2. So what's a basis for my eigenspace? It's just the set with the vector 1, 1, 0. Yeah? So here is one of my eigenvectors. Let's find 2 more. What if lambda is equal to negative 1? If lambda is equal to negative 1, then whenever we do A minus lambda I, so we're going to subtract negative 1 on the diagonal, we should get 3, negative 2, negative 2, 3, negative 2, negative 2, 2, negative 2, negative 1, augment 0, 0, 0. Perform some row reduction, and it looks like you get 1, 0, negative 1, 0, negative 2, 1, 0, 0, 0. So, what's our free variable? I know that we have pivots in x1 and x2, so my free variable must be x3. x2 looks like it has to be 1/2 t, and x1 has to be t. That's 1/2. Yeah? So what's a basis for my eigenspace? It's the set with just the vector 1, 1/2, 1. Another possible vector that you could have put in here is 2, 1, 2 by scaling it by a factor of 2, right? So if you prefer no fractions, you could have also had the basis be the set 2, 1, 2. Yeah? You get to pick. And remember, bases are highly not unique creatures. We just need to pick one of them. And let's find a basis for the eigenspace corresponding to lambda equals -2. Whenever we compute a minus lambda I, looks like we get 4, -2, -2, 3, -1, -2, 2, -2, 0. Whenever we perform some row reduction, and I hope that you're all good with this row reduction. If you're not, please reach out to me and we can go over this together. Yeah? We should get 1, 0, -1, 0, 1, -1, 0, 0, 0. Oops, augment 0, 0, 0. Yeah. So here I see that x3 is once again free. I know that x2 is going to have to be t. x1 also has to be t. So a basis for this eigenspace is just the set 1, 1, 1. Yeah? So what can we do with this? We have 3 distinct eigenspaces. Yeah? I know that any eigenvector from each eigenspace has to be linearly independent. Yeah? So I know that certainly our basis vectors have to form a linearly independent set. So I know that a basis for Rn, n is 3 here, is going to be the set of vectors 1, 1, 0, 2, 1, 2, 1, 1, 1. These are vectors. Sorry about that. The set of these 3 vectors forms a basis for R3. And that's kind of interesting. And these vectors, of course, are eigenvectors corresponding to lambda equals 0, -1, -2. So how can we use this to diagonalize our original matrix? We know now that our matrix A will be equal to the matrix 1, 1, 0, 2, 1, 2, 1, 1, 1. Here's my matrix V, right? That's my matrix of eigenvectors. Here's my matrix D here, which is 0, 0, 0, 0, -1, 0, 0, 0, -2. And I'm going to be lazy and just write V. And I'll put the inverse sign. Yeah, we know how to compute inverses. How do we compute inverses? You augment with the identity, row reduce, whatever. But we can just put it here and just leave it as something inverse. We can compute this if we really wanted to. Yeah. And now it's diagonalized. We have found a similarity transformation between A and the diagonal matrix with just the eigenvalues on the diagonal. And let's just note here, what if they weren't distinct? Then the sum of the dimensions of the eigenspaces would have to equal whatever n is. We just put a basis for the eigenvectors in V, and you repeat the eigenvalues along the diagonal of D according to their algebraic multiplicity. Okay? Same process. So who cares? Yeah, who cares? We know that A and D will, of course, have the same determinant. And what's the determinant of A? Well, it's the determinant of D. And what's the determinant of this diagonal matrix? It's a product of the eigenvalues. And we've proven that before, right? So that's kind of interesting. This gives us another proof for the fact that the determinant of A is the determinant of D, right? Since they're similar. And what's the determinant of D? It's just the product of the eigenvalues. So this gives us another proof of that fun fact. We also know they have the same characteristic polynomial. That's true in general. But one really cool thing that this is actually in applications. This is actually really cool for us in applications. So first, suppose A is invertible. if A is equal to V dV inverse, what do we know